So we're in chapter 7 8 and we're looking at chemical bonding, and we're going to combine chapters 7 and 8 because there's really no clear differential between the two of them. So when we talk about chemical bonding, we need to look at covalent and ionic bonds. And as we look at these, we need to look at what makes a covalent versus an ionic bond, how we tell the difference, and how it leads to the properties of the molecules as we go through this chapter. We know sodium chloride is ionic, and when we write the formula for NaCl, we do remember that this is the simplest ratio of sodiums to chlorides. So if we look at our sodiums and our chlorides here, we realize that we are making a massive three-dimensional compound up of sodiums that are going to be surrounded by chlorides, and this is going to be going on in each direction in forwards and backwards, and that each of these is, quote, bonded, in this case, with a nice ionic bond. And remember, ionic bonds occur between ions, and ions here are going to have the positive and negative charge, and this electron that we would have started out with the sodium has been transferred to the chloride, and these guys stick together in massive three-dimensional structures. So, how do we know how things bond? Well, we have three different kinds of bonds. We are going to look at ionic, and we're going to look at covalent. But when we go into covalent, we have a couple of different varieties. We have a nice pure covalent, and we have a polar covalent. Now, pure covalent means that the electrons are shared equally. So if we had something like chlorine bonded with another chlorine, each of these chlorines wants electrons the same amount, and when we put these guys together, we're going to have a pure covalent bond, and the electrons will be shared equally. On the other hand, if we put a hydrogen with a chlorine, we know that from the position of hydrogen on the periodic table that it doesn't want electrons. If we go back to our electron affinity, it is not wanting electrons as much as the chlorine is, or stabilized by the gain of electrons as much as chlorine is. And therefore, the electrons that we put inside here with our nice covalent bond are not going to be shared equally. And we're going to have a polar covalent bond, meaning that the electrons are going to, on average, spend more time around the chlorine than they are around the hydrogen. This is going to change what the properties are. We're going to have a partial positive on hydrogen and a partial negative on chlorine, and this little partial sign just means a little. So it's going to be a little positive on hydrogen and a little positive on chlorine. The electronegativity scale was introduced by Linus Pauling. He made a number of contributions and was a Nobel Prize winner in chemistry. And what he said that fluorine, if we look at it on the periodic table, is going to be the most stabilized by the gain in electrons, and it is going to have the highest electronegativity. We're going to shorthand electronegativity as an En, and an electronegativity is the electron withdrawing power of an atom within a bond. So electronegativity means that if I put something like hydrogen next to fluorine, fluorine has a high electron negativity, and it is going to pull these electrons towards itself. The higher the electronegativity, the more it's going to pull electrons towards itself. At some point, it's going to pull the electrons off, and that will give us ions. Our scale here for electronegativities puts the most electronegative element over here as fluorine, the least electronegative down here as our group 1 element, so we can see our trend here, and our electronegativity is going to increase as we go up and over. Note the noble gases are missing, and the noble gases are missing because we know they are not going to want to pull electrons towards themselves. They're not going to gain electrons. So our most electronegative element is fluorine. So what happens when we take and we put elements together? What sort of bonds are they going to make? So if we look at our electronegativities, if the electronegativity between the two bonding atoms, and we do this for each pair of atoms that we have in our molecules, if their difference in electronegativity is 0, we say that the bond is purely covalent, which means that the electrons are going to be shared equally. That's going to be the case where we have any two things that are the same bonded together. The say hydrogen bonded to hydrogen, upwards as close to as carbon bonded to hydrogen. Carbon bonded to hydrogen, the electronegativity difference is small enough that we're going to say that these electrons are shared equally and we have a pure covalent bond. The closer that value gets to zero, the more purely covalent that bond is. So hydrogen H2 or chlorine or anything that has the two exactly the same electronegativity is going to be the purest or the most equally shared electrons. Now, if the difference in electronegativity is large, we tend to define that as greater than 1.8. We say that the electron is in fact transferred. So if we put fluorine next to a sodium, these have a massive difference in electronegativity, and the fluorine is simply going to take this electron from the sodium and make an Na plus and an F minus, and we're going to have an ion. Now, if it is in the middle, and we define in the middle in general as between greater than 0.4 and less than 1.8. So if the difference, delta En, difference in electronegativity between two bonding atoms, is less than 1.8 and greater than 0.4, we have a polar covalent. Polar means as in a dipole, as in two ends, meaning or two different charged on the end. So if we had for the difference, let's say HCl, these guys have a difference in electronegativity. It is less than 1.8. And if we looked at these, chlorine would pull the electrons a little bit towards themselves, not enough to ionize, giving this a small negative, which we call partial negative charge, and leaving hydrogen with a small positive or a partial positive charge. Now, this is going to dramatically affect the properties of these molecules, and we'll deal with that a little later. So a quick note on how we look at our covalent bonds. So if we imagine that we have two atoms here and they're free in space and they're separated. So we've got our two atoms right here. And we are going to imagine bringing these guys in together. So I want you to consider hydrogen bonding with a hydrogen. Now we start looking at our theory. We're going to assume that our hydrogen has its electron in its atomic orbital. So each of these hydrogens have an electron in the 1s1. And 1s1 we know is a nice little spherical orbital. We have the nucleus here in the center. And this electron we know is a cloud somewhere outside. But for the sake of argument, we're going to use our little arrows. And we're going to put this one as an up and this one is a down. So we can obey our Pauli exclusion principle when we go through. And we're going to take these guys and we're going to bring them together. Now, when we bring them close enough, they're going to start to interact. And as they start to interact, those atomic orbitals are going to start to overlap. And when they do, with our nuclei here, our electrons can be shared with both of these individual atoms. This sharing of the electron is going to be our covalent bond. And when we say that we've got a covalent bond between these guys, this is what we are looking at. Now, we're not going to draw these out because they're a pain, but here, if we are too far apart, it's not going to share. If we are too close together, the nuclei will bump into each other. But if we're the right distance apart, we're going to get an overlap in the atomic orbitals, and we're going to make a covalent bond. Bond length is the distance at which the lowest potential, most favorable energy is achieved.